Okay, so we've been talking about thermodynamics, and I want to put everything we've talked about in one chart. So we said to see if a reaction is going to happen or not happen, we have to look at delta H, delta S, and delta G, right? And if delta H is negative, that means it's an exothermic reaction, and delta S is positive, that means we are going towards this order, and this order is favored. That means that delta G is going to be negative, which means the reaction is going to happen, because delta H negative is favored. Delta S positive, if it is favored, is good if we release energy to the surrounding, and is good to be disordered. It's easier to be messy. So we have favored, and then the reaction will go. Now, on the other hand, if delta H is positive, that means it's an endothermic reaction, so it's not going to be favored. And delta S is positive, which means it's going to be ordered. What that means is the delta G will not go, because if you have not favored and not favored, it's not going to happen. Now, what happens if one is good and one is bad? For example, delta H is not favored, but delta S is favored. Or delta H is favored and delta S is not favored. Then what would you do? Then what you have to do, you would have to calculate what? Then you would have to calculate delta G, right? Then you would have to calculate delta G, and then if delta G is negative or delta G is positive, if the delta G is negative, the reaction will go. Positive, the reaction will not go. So you need to calculate delta G. If one is good, one is bad. If both are favored, it will happen. Both are not favored, it will not happen. But one of each, you would have to calculate it. And when that happens, okay, the temperature then will matter. The T will matter. Then the temperature will matter because of the way the equation is set up. Okay, so this is kind of summarizing what we've talked about so far. Enthalpy and entropy to figure out if the reaction is going to happen or not going to happen. Basically, when you're calculating delta G, you're looking at the balance between delta H and delta S. Okay, now let's talk more about this delta G. That's going to be today's lecture. 3 ways to find delta G of a reaction. There are 3 ways to do this. The first one, you already know. If you have delta H and delta S, then you know how to figure out delta G. The Gibbs free energy, right, is delta H equal minus T delta S. And we talked about that reaction a lot last time. Now, another way to figure out a delta G, if you can figure out the delta G values in a table, take them from a table, and then what you would do, what we've done before, product minus reactant. We've done those many times. The first 2 you know. Now the third way to figure out delta G is a new one we haven't talked about. Delta G equals minus RT ln of K equilibrium. Alright, now this is the one that we're going to talk about. Now, K equilibrium, that's the equilibrium constant. That's an equilibrium constant. Now, let's talk about this a little bit. If you remember, when we have equilibrium, we have A going to B, okay? And equilibrium is always product minus reactant, okay? Now, again, equilibrium constant, we're trying to reach equilibrium. Now, energy is a driving force for reactions. So the tendency for a reaction to reach equilibrium is driven by Gibbs free energy. So Gibbs and equilibrium constant are related, as I showed here. Again, that's because the driving force for reaction to reach the equilibrium, there's the energy associated with that, right? So the tendency for reaction to reach equilibrium is driven by delta G, because energy is the driving force for reaction to reach equilibrium. So there is and this is the equation to relate delta G and equilibrium constant. Energy and equilibrium constant are related. Okay. Now, remember what we talked about. What does this mean? That means a standard condition. That means standard condition. Okay. Now, what that means is, again, I want you to remember what we've talked about before. When delta G is negative, you have a spontaneous reaction. Okay? Now, when K is bigger than 1, that means what? Look at this reaction. If K is bigger than 1, that means what? That means product is favored. So the reaction will happen in the favor of the product. So I want you to remember these two, because delta G negative, spontaneous reaction, K is larger than 1, that means product is favored. Those are good things. The reaction will happen. Now, I mentioned over here that remember that this one is standard condition. This one is a standard condition. Now, what happens if we are not at a standard condition? Now, if you're not at a standard condition, the equation that you can use is delta G equals delta G naught plus RT ln of Q. So we can use this when we are not at a standard condition and the system is trying to reach equilibrium. That's why you have Q. You haven't reached equilibrium. You are trying to reach equilibrium. Okay. Now I want to summarize this again. So remember, if delta G is positive, the reaction is not really it's not favored spontaneously. So what is favored is what? It shifts to the reactant. The forward reaction, the backward reaction is favored. Now, if delta G is negative, that means what? The reaction is favored towards the product. Okay. Now, what happens if delta G is 0? The system has reached equilibrium. The system has reached equilibrium. So I like this because it kind of puts what I just talked about in perspective. So delta G is positive, it's favored the reactant. Negative, so in the product, the reaction spontaneously is going to go. Delta G is 0 is you reach equilibrium. And this is why I wanted to show you why that delta G and K equilibrium are definitely related. Okay, and here this is when it's not a standard condition and you're trying to reach equilibrium. That's why you have Q, because you haven't reached the equilibrium yet. Okay, now the best thing to do is let's do a practice problem to get this right. Here's our problem. So here's our reaction over here, and the question is, will this reaction go forward or reverse at a standard condition? Now you have to look at delta G, right? We talked about that. If I look at the delta G, my delta G is positive. If a delta G is positive, what does that mean? This is a non-spontaneous reaction, right? It will go the reverse. It was going to go reverse. It's going to go back to the reactant. We talked about it here. Because delta G is not favored, it's going to go to the reverse reaction. So far, so good. Okay, so that part hopefully was easy. You got it down. Let's look at the second part. It says calculate delta G. And it asks you to calculate delta G at 343. So what that means is we are not at a standard condition, are we? We are not at a standard condition, right? Condition. We are not at standard condition. Do you agree? So if I'm not at a standard condition, what did we say? We say here's the equation. Delta G equals delta G naught for standard condition plus RT ln of Q. Again, why does it have Q? Because we may or may not be at equilibrium, right? We may or may not be at equilibrium. Okay. So what that means is I should first figure out Q. Now, Q is the same as before, product over reactant. But it gave me ATM here, but that doesn't matter. So it will be the pressure of C3H8 times the pressure of H2 to the power of 2, because coefficients over matter, right? And the pressure of CH4 to the power of 3, right? Because you always raise it to the coefficient. Okay. Now, I know how to do this. This is we've done many times. So then what I would get is 2.4 times 10 to the minus 5 times 3.5 times 10 to the minus 8 to the power of 2 over 2.7 to the power of 3. If I do that, what I end up getting is 1.4937 times 10 to the minus 21st. Okay, I figured out Q, right? I figured out Q. Now what I have to do ln of Q. I'm just going to do it right now to make it easier. So it's minus 47.95. We're good so far? Okay. So I'm going to rewrite this equation here so I can plug it in, because I never actually went over each component with you to figure out the unit. Okay. Now, do you have the delta G? You do have the delta G. Now, before you tell me what the delta G is, this R constant really, really matters. What is this R constant? This R constant is 8.314 joules over mole Kelvin. So, what does that mean? I am bound to having joules, right? Because remember, the constant will dictate our units. So again, what that means is I'm bound to that. So what is my delta G? I have to convert it to joules. I had it in kilojoules. I want to convert it to joules. 130,100 joules. Okay. So plus, now my constant is 8.314. That's great. That's also joules mole Kelvin, right? Okay. Now my temperature is 343. So it's what just happened? 343 Kelvin. Now my ln of Q, I already put that in, is minus 47.95. So far so good. Okay. So, my God, what does this keep happening? If I plug everything in, what I end up getting is negative 6,647.8 joules. And I usually like to convert it to kilojoules sometimes, but sometimes I can keep it that way. It's fine. I am limited to 263 though. So here is 6,600 joules is going to be my answer. So far so good? Okay. So, what are you thinking about this problem? Which way the reaction is going to go? Forward or reverse? It's going to be a forward reaction because I have a delta G that is negative. So far so good? Alright, beautiful so far. Now, the next thing we're going to do, I'm actually going to go over some kind of fun problems. I think they're fun. We're going to do some practice problem with you figuring out delta H, delta S, and delta G without doing any calculation. So water liquid goes to water gas. Okay. And this is at 25 degrees Celsius. Ready to do this? Now the question is, what is a delta G? What is a delta H? What is the delta S of this reaction? Okay, let's do this. Now, the first one I want to do delta H first, okay? Now, I taught you guys in Chem 1A that in Chem 1A I said, whenever you have these phase changes, put this up. Hopefully you remember that. I said when you're going down solid to gas, you're an endothermic process. When you are going up, you're an exothermic process. Hopefully you remember that. Okay. Now here, I'm going from liquid to gas, right? I'm going from liquid to gas. If I go from liquid to gas, that's an endothermic reaction. That's an endothermic reaction. And it makes sense because you need energy. You need to heat up water to go to gas, right? So you already knew that because you need to heat up water to go to the gas phase. Perfect. So you already knew that. Now here, I go from liquid to gas. Do you agree that you're becoming more disordered? You are becoming more disordered, right? That is favored. That's delta S is positive. Okay. Now, what's going on here? Because my delta H, not favored, my delta S favored, what is going to happen to my delta G? Is my delta G going to happen or not happen? Here's a hint for you. Look at the temperature. At 25 degrees, will water liquid go to gas? No, not really, right? You have to be a lot hotter than that in order for that to happen. So the delta G is going to be positive. It's not really going to happen. Why is that? You have to look at the temperature, and that's why. So far, so good. Okay. Again, one more time over here. You have to put in energy for water to go liquid to gas. You already knew that. All right. Now let's look at the next one. You ready? Let's look at the next one. Let's say I have H2O liquid wants to go to H2O gas, and I am at 110 degrees Celsius. Okay, do this one on your own. So delta G, delta H, delta S. It's probably best to do delta G last. Okay, you ready to do this? Hopefully you paused me and you did it. Again, the same thing as before. Always I write down solid, liquid, gas. You come down endo, you go up is an exo. And it makes sense. To come down, you need energy to make solid go to liquid, liquid go to gas. My delta H, I have liquid going to gas. So what is my delta H? My delta H is positive. I need energy to make that happen, right? Liquid going to gas, that is positive. Okay. Now how about delta S? What's going to happen here? I went from liquid to gas. You agree? So delta S is also positive. Okay. So this is not going to happen. This is going to happen. What's going to happen to delta G? Now you have to pay attention to the temperature. You have to pay attention to temperature. When one is favored, one is not favored. We talked about it. Temperature matters. At 110 degrees, will water go to gas? Absolutely. At 100 degrees, water will boil, right? So in this case, yes, this will be negative. This will be go. Because again, the boiling point of water is what? Is 100 degrees. So this will definitely happen. Okay, beautiful. Now, we are going to finish up this chapter with a very fun practice problem. And you'll see why I say it's fun. It's a good problem, but it also have a little bit of real life stuff, which is always fun to have. So here's our next practice problem. Here's a problem. So this is interesting. Toyota and Honda, they were advertising this and were saying our cars run on H2 and O2. This is green energy. So instead of using gasoline, we have H2 combined with O2, produces water, and that's what our cars run onto. And yeah, when you look at this, you go, wow, this is amazing. Clean energy is good for the environment. And they had this on their website, and they were advertising this clean energy cars that they have. The problem is, A chemist would look at this and go, wait a second. This reaction is great, but the problem is the production of H2. Where is the H2 is going to come from? Okay, so here is a reaction that is going to produce an H2. Here's a reaction that is going to produce an H2. Now, what I want you to do, if you have all these numbers, so you pause me and do this, and figure out the delta H of this reaction, the delta H of this reaction, do product minus reactant. Figure out the delta S of this reaction, you do product minus reactant, and figure out the delta G of this reaction, again, using product minus reactant, because we have all the values. Do this. If you do this, what you get 131.3 kilojoules. Make sure you do it on your own before you copy my number, okay? Joules per K is for delta S, and then for delta G, you get 91.4 kilojoules of energy, okay? So, if you look at this, look at the delta G. Well, this reaction for delta H is not favored. Delta S is favored, but your delta G is not favored. Okay, favored by entropy, but not so much by enthalpy. When you combine it together, delta G is positive. So the reaction, it would not happen without. The reaction would not happen without doing some work. So this reaction would not happen without doing some work, right? Okay. So let's do a practice problem and say, at what temperature would this reaction happen? At what temperature would this reaction happen? Okay, you know how to do this. We know delta G is equal delta H minus T delta S, right? At what temperature would this reaction happen? Okay. Now, that is to say basically when is the delta G negative? To get a general idea what we can do, we can set the delta G to be to 0, just to get an idea, right? So after 0, then it's going to be negative. So again, is there a temperature at which this reaction might happen? Because right now, this reaction is not favored. Delta H, not favored. Delta S, yeah. But when you put it together, delta G is positive. This reaction is not going to happen without doing any work. Now the question is there a temperature at which this reaction might happen? When can we make the delta G to be negative? And we can get a general idea by using this Gibbs equation. Now, right before delta G turns negative, it first has to be 0. So we can use 0. Let me repeat it again. So right before delta G turns negative, it has to be 0. So we can use 0 to figure out if there is a temperature. Okay, I'm going to use kilojoules minus T, all right? Now, for delta S is joules. I have to be consistent. So what I'm going to do, I'm going to convert that to kilojoules. So 1 kilojoules is 1,000 joules. You guys see what I did? Okay. So then the joules will cancel out. And then this is kilojoules. It would match up the kilojoules over here. Now, I'm trying to solve for T again. Now, what I get for T, I get 980 Kelvin, which is 707 degrees Celsius. So I have to use energy from another source to heat up this reaction to produce the hydrogen. So again, it will greatly depend on the source of energy, but this reaction has a disadvantage that it uses coal and produces carbon monoxide. So you have to be very careful. This is the temperature that it needs for the reaction to happen. I have to use some sort of sources to get to that temperature. So careful when they say clean energy and they say clean energy cars, which is so popular nowadays. Look at the reaction. Think about it. It's like, let me do some math and see if this clean energy is actually clean energy. All right, beautiful. Nice job. We're done with thermodynamics.